If we just present the truth, an organized PowerPoint with all the things logically constructed and put together with the series of demonstrations, we've got to get away from that. We cannot just continue to just all the stuff to them and then they give it back to us, because they won't. You as the teacher are organizing everything for their brains. We must not do that. Guided dialogue. Let's learn physics. My students have a lot of misconceptions. I mean, I have a lot of misconceptions too, but my students have a huge number of misconceptions about physics. Projectile motion is complicated. And with complicated topics that students often misconcept, we need to take a different approach. If we just present the truth, like an organized PowerPoint with all the things logically constructed and put together with the series of demonstrations, it turns out that what feels good to us and what looks good to a regular educator is not good. Educationally, what we need to do is draw out their ideas. Just bring them all out. Just put them all out there. And then they as the learners need to consider their ideas, reject some of their ideas in the process, and strengthen other ideas. That's the way real learning works. One way to do this is a guided dialogue. It is a slow and meandering and difficult process. It requires a lot of knowledge and preparation on the part of the guide. It's really worth it, and they learn a whole lot. When done well, this kind of dialogue allows students to take far more enduring understandings. Brain images and logical threads. Their brains need to do the work. We must not do that work for them. What you're going to see here is an honors physics class. They're actually really good. We've just finished one whole semester together. They've taken the midterm exam, and we have covered things like Newton's laws of motion and velocity and acceleration. We've put arrows all over everything. They know free fall and centripetal force. They've done static equilibrium and inclined planes and friction force. They have sketched free body diagrams for months, and they can solve some pretty tough math problems. But when you ask these same really good students to apply all that they know in a free format to this new topic of projectile motion, even if we've done all the pieces, they have a lot of difficulty putting that together. And that's what we want. We want them to take this knowledge that they have and apply it to a new situation. And it's tough. Projectiles. You know all about projectiles, right?
Nope.
Nope.
You know nothing about projectiles. Have you read about projectiles yet? Oh, wait, so I didn't assign that at all?
You did not.
So you know nothing about projectiles, except you know a whole lot already. What we're going to do is fill in all the things that you know already about just, physics and projectiles and stuff. And it's all about these. The little ball, tennis ball, will be thrown around at you randomly. So pay attention, because this ball could come at you at any time. Nice catch, by the way. So the ball's flying around, and what is it? Come on, catch the thing. That's pretty talented right there. So the ball, as the ball is flying through the air, ball flies, right? Ball is flying through the air. The ball, as the ball flies through the air. Tell me about it. You know all this physics stuff, right? Tell me one thing.
Parabola?
Parabola. That's a possible shape. Let's talk about possible shapes. Is it a parabola? What's another name for the shape of that thing? We got parabola, we got... Parabola is a correct answer from a smart kid. But what about the rest of their minds? Just get those answers out. Eventually, we'll get the right one. We will. Together. Half circle. We got a parabola, we got a half circle. Oh, you're giggling at that, huh? Oh, good. Go ahead, give us a better one.
Ellipse.
Ellipse.
Oh.
So we got the parabola, the ellipse from that gravitational satellite thing, right? So we got ellipses on the notebook, nice. So we got the ellipse, we got the half circle, we got the parabola. Eddie?
Also a name.
Just another name. It doesn't have to be a technical name.
Just nothing.
Throw it back at me. Come on.
Okay. Could be a rainbow.
A rainbow! And what's at the end of the rainbow, everyone?
Those Irish people.
Those Irish people and the gold bucket.
An orc.
An arc. We got a whole bunch of terms that could. Anything else? You think of it? We got another term. We got arc. We got rainbow, and the kettle of gold, and the parabola, and the ellipse, and the half circles. Oh, a whole bunch of different things. Okay, tell me something else. Ready, go. Anything else about projectile? You're in physics? Come on, tell me something.
Whoa. Oh, look, there's.
Keep going, come on. Oh, the velocity decreases as it goes up. Okay, more about the velocity. More about the velocity.
Air friction.
Air friction. Is there a little bit of air friction? Air friction. That's really important in many real-life situations. So we'll consider it sometimes and ignore it most of the time. And then we'll consider it again. Depends on the situation. You'll see as this lesson unfolds. Are we going to pay attention to that closely? No. Why won't we?
Because it's too hard.
It's just too difficult. It makes physics way too difficult because physics as it is pretty easy. So we don't want to make it too difficult. So we eliminate air friction. We're not going to pay any attention to air friction. And what about, tell me something else about the velocity.
As it goes down, like as it falls, its weight is like it's accelerating down.
So on the way up, its velocity is decreasing. And on the way down, this is what you're talking about over here, right? So the velocity is increasing. It's accelerating down. And you had something else? It's something about the direction. 1 for 3. It's good.
It's pretty good considering.
Anything about projectiles that hasn't been mentioned yet?
That's a good question.
Something about physics and projectiles. Anything?
Would you accelerate?
Acceleration is constant.
Acceleration is constant. Oh, we got what? Why would you think acceleration is constant?
Because it is.
Because it is.
If we're ignoring air friction, then the only net force acting on it after it's been projectiled is
After it's been okay, let me
is
see.
the weight.
After it's been projectile. So after it's been projectile, the only force acting on it is its
weight.
weight. Okay, so we got that. Got the velocity. What did you say about the acceleration?
Would it be constant?
Constant acceleration. Look at that. Those are good answers, but only from individuals. Just because you get an answer from a couple of people doesn't mean that everyone understands. Always test in various ways over various days.
Because, like Marcus said, after the initial force and not taking into account air friction, it would just be weight.
The acceleration's always down.
Acceleration's always down. You made it halfway. That was good.
I was going to say acceleration. I was going to say the same. That's what I was going to say.
Get a piece of paper. Piece of paper to write something on. You're going to draw random stuff on a piece of paper. So pull out your professional notebook. For each of those points, all 5 of them, your job for the first one is sketch a free body diagram for each of those points. Second one, velocity. Bunches of arrows. This is the most complicated one I saw. And just repeat it all the way through. So you have this, and that, and that. Anything wrong with that? Matt, what's wrong with that?
There's no force because there's any hurt. It's not touching anything.
So it's not like resting on a surface, right? As this thing, as the thing flies through the air, as it is, while it's flying through the air, while it's flying, after it leaves my hand, that's when it becomes a projectile. There is nothing pushing up on that. So there isn't any up force. So if you have an up force on there, that thing doesn't exist because you just had it's flying through the air. You're not still supporting it. You are not still pushing it.
There shouldn't be any force to the right because it's not accelerating to the right. It's just continuing to the right because of inertia.
And this is after it leaves my hand, right? So after it leaves the hand, and as a couple of you mentioned, after the initial projectiling, after it is projectiled, you take that thing, it's just flying through the air, and as it goes through the air, there isn't any force that's applied horizontally to it. So that thing doesn't exist. Sometimes here, you let them eliminate correct answers, and then others correct the corrections. Sometimes you let the wrong answer stand just to see what they'll do. Sometimes you, as the teacher, give wrong answers just to make them think and analyze more. But watch this. They actually get pretty good at details as they practice throughout the year. Anything else wrong with that?
The weight's constant throughout.
Weight's constant, which means what?
They would all be equal.
Same-
Or same magnitude.
Well, would they be
and
equal
same
also?
direction as well.
Same. So using good terminology, can you say that those things are all equal to each other?
Yeah.
Yeah, same size, same magnitude, same direction. So every single one of those should be exactly the same size. And this one, I drew it intentionally significantly longer, but these are all that's the weight, and this is too short. So that's the weight, and that's the weight, and that's the weight, and that's the weight. They're all weights, and you can label them as this. It's all the exact same size all the way through. So those are your weights, and that is the free body diagram for every one of them. If there's air friction, does it make it a whole lot more complicated?
Yeah.
Yeah. While this thing is flying up in this direction, what's the direction of the air friction acting on the ball? Straight down?
Like opposite to
So opposite, it's what? Opposite the direction of its... Good physics word. Come on, you know this one. Opposite the direction of its... Mike? Velocity. So velocity is in that direction, so the friction force would be opposite that, but then the friction force changes. Friction force is just always going to be opposite the direction of motion. And what is the net force? Allie, what's the net force in all those cases?
the initial throw.
The weight. Anything else? Are there any other forces involved? No. After the throw, and this is when the projectile starts, is after the throw, the only force acting is the weight. And if the only force acting is the weight, then that is the net force. You have the net force, and the net force, and the net force, and the net force, and the net force. And does this thing have a mass?
Yeah.
Probably. It's an object. It probably has a mass. And so what big principle, what equation, what law are we working with here? What? Say it louder. Newton what? Go second, yeah. So Newton's third law, you have two objects interacting. While that was being thrown, that is Newton's third law application. If you include here the earth pulling that down, causing the weight, that is a Newton's third law application. But with this one object, you're just dealing with Newton's second law. And what is Newton's second law?
Net force equals mass times acceleration.
Net force equals mass times acceleration. So net force is equal to the mass times the acceleration. What is the net force? It's the weight. You told me that already. Mass times acceleration. And so what is the acceleration of this
9.8
thing?
meters per second per second.
What?
9.8 meters per second.
9.8 meters per second
Or
every
10.
second. Round it off to 10, right? But this is that's the weight. So weight mg is equal to ma. Does this look exactly like what you did before? What we did before for objects just like falling and being thrown upward? Any different forces? No, it's exactly the same situation, except that it's now being thrown horizontally, but the acceleration is the same. So A equals g. So what is the direction of the acceleration? What is it?
Straight down.
Didn't even mean to do that. It's down, right? Because if the weight is down, and that's the only force applied, the acceleration, because this is a vector equation. This little acceleration right here, that's a vector, that's a vector. Those two must be parallel to each other, exactly in the same direction. This acceleration has to be g, and that is down. This is a reminder of the Freefall Acceleration they did recently. And it's a setup for tomorrow's diagram. But they'll still often get it wrong. So what's the acceleration here, and here, and here, and here, and here? It's all exactly the same thing. Its acceleration is g, whatever it happens to be. Here it's about 10 meters per second every second, about 22 miles an hour every second down. Parallel with that thing. Now you got some really funny diagrams over here. Some of you have velocity acting down. And with some changes in size. And some of you have velocity acting up. And some of you have velocity acting horizontally. This is the most entertaining diagram. And some of you have the velocity acting kind of like that. That. Actually, that corresponds. And then this, that. Okay, so what's wrong? No, what's wrong?
Velocity can't be going all those directions.
Okay, so first of all, it can't be going in all those directions. The velocity is in one of those directions. Could we split the velocity into its components if we wanted to? Yeah, we're going to do that later. But the primary velocity has one direction. Which one direction does it have? But more importantly, let's eliminate the directions that are wrong up there. Peter?
Down.
Down. Why is it not going down?
Because it's not.
Thank you. Yes, it is clearly not going down. And so all these down things, no, that's the acceleration. And please, as is common, do not confuse force and velocity and acceleration like you have all the time and we do all the time. That's something you can't do. The acceleration is down, but that is not the velocity. Not going to be that one. What else is wrong?
The up one,
Why is the up one not correct?
because it's not like traveling perfectly straight up. So
If it were doing this, then it would be straight up and down. But it's not straight up and down, so it's not going to be doing that. So it can't be. And you can think your way through these things, like we draw a whole bunch of arrows and then eliminate stuff. It's not that one. It's not going to be the up. Okay, what else is it not going to be? Brandon?
Going up to the right.
It's not going to be going to the right. Is it going to the right? I mean, it's going to the right, but that's not the whole velocity. If it were traveling exclusively to the right, what would it be doing?
Floating horizontally.
Floating horizontally, just moving along, or like a bowling ball rolling along the floor, right? So bowling ball rolling along the floor, which I should pull one out, but the bowling ball rolling along the floor is what it would have to be. It's definitely not doing that. It's definitely not doing that, right? But it is. If you know anything about projectiles, you know that horizontally, that's what it's doing, and vertically, it's a free fall cliff problem. But sometimes you state the false and then let them correct it, or correct it 3 days later. It's fine. They'll get it. Be patient. Use several days. Let them think. And so the velocity is, and you know this term already,
Tangential.
at a tangent. So the velocity is at a tangent to the curve. V at a tangent to the curve. What else is wrong? Nate, what else is wrong?
They're not all equal.
They're not all equal. Where is the speed? Where should the arrow be the longest, Nate?
Probably at the last one.
Last one. The arrow's biggest over here, so make this one a nice big one. And tangent to the curve, nice and big. This one's a little bit higher, so it's going to be smaller. Where should it be shortest, Nate?
At the top.
The very top. So as it goes up, tangent, shorter tangent, really short tangent, longer tangent, pretty similar to that one in size, and then longest tangent in that direction like that. And what is this thing doing? As it flies through the air, what is its speed doing? Michael, what's the speed doing as it goes through the air?
It slows down when it gets to the top and it speeds up.
Slows down on the way up and speeds up on the way down. As you can see with the little arrows right there, because the velocity is speed with direction. Now watch this. It's pretty cool. It's a setup for the discussion over the next several days. What is it also doing? What is that velocity also doing? Changing direction. Wait. What is the name for that changing direction acceleration?
Centripetal acceleration.
Oh, you got a centripetal acceleration. Do you also have a tangential acceleration?
Yeah.
Yeah. So it's kind of a combination of a whole bunch of different things that we've done already. This velocity, this projectile stuff, is normally done at the beginning of physics. Like at the very beginning, before you know anything about physics, before Newton's laws, before anything. Is that a good place to put it?
No.
No, this is complicated stuff. And tomorrow what we're going to do is get into the proper, the stuff. We're going to get into the reasons why we solve the things the way we do and how we're going to break it down. This is a really complicated thing. But again, there's only how many forces acting on it? Just one. You have one force acting on it. We're going to use this thing to help us solve for all the problems that we have. But it is a complicated combination of centripetal acceleration toward the center, caused by a centripetal force toward the center, splitting these things into their components. We're going to split all that stuff into its components, and it's going to be a good time. That was a cold introduction to projectile motion. And a lot of the students had good diagrams on their papers, but a lot of students, even after hearing the properly described answers, when you got to a diagram, they get confused among force and acceleration and velocity. This is a tough thing to translate words into diagrams and diagrams into words and a real physical object and a real physical situation into something that we're doing in physics. I mean, physics is super practical, but it's tough. These things right here all represent misconceptions. None of these diagrams are correct, and there are some that are subtly wrong and some that are just like, oh goodness. After the end of that first 20-minute introduction, I gave them the assignment to go home and read 2 sections in the book on projectile motion. Everything the book has on projectile motion. Take notes, because they're used to doing that. Take some notes, write some good diagrams down, really struggle with the thing. Answer about 10 quick questions at the end of the chapter. No problems to solve, just answering questions and thinking about the concepts and seeing the diagrams. Part 2, they get better. They're quicker. Part 3, they're quicker still. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.